Welcome back to our series on numerical analysis. Today we're going to walk through an example of using the backward Euler method in MATLAB to approximate the solution of y prime equals 4y from 0 to 3 seconds. We're going to use an initial value of y naught equals 1. We're going to compare our numerical solution to the exact solution, which looks like y equals e to the 4t, and we're going to test different dt values to see how that affects our solution error. Very similar to what we did for the forward Euler method. Okay, so just to start, we're going to start with discretizing our time, just like we did in the last video. Hope I spelled that right. Okay, so we're going to say dt equals 0.01 seconds. We're going to say t naught equals 0, and t final equals 3 seconds. And then we're going to say our time is equal to our initial time to dt tf. So we're going to go from 0 to 3 seconds in steps of dt. Okay, and then we're also going to say our initial value, so y of 1, is going to equal 1. I'm going to run that. Okay, everything's working. Good to go on from here. So let's talk about the backward Euler method here for a second. And let's recall our equation. So the equation we derived in previous video is like y of I plus 1 equals y of I plus delta t times f of y I plus 1 comma t of I plus 1. Okay. For this particular example, our function is 4y, so we're going to replace this f with a 4 times y of I plus 1. We don't have any t in our function. Okay, so this is our backward Euler formula in this case. Now we're going to be using a function called fzero. You can also use a function called fsolve. And in order to do that, you have to set the left side of your equation to 0. So we're going to do the following. We're going to say 0 equals y of I plus dt times 4 times y I plus 1 minus y of I plus 1. Okay? And now what we're going to do is we're going to define a new variable for y of I plus 1. We're going to call this capital Y. We're going to see why we have to do that in just a second. But this is the formula that we need. We need a formula where 0 is on the left side, and then the only terms on the right side are y of I, which we're going to know for any time step, and a big Y, which we're going to solve for. Okay? So now we're going to create a for loop. So for I equals 1 to the length of t minus 1, just like we did for the forward Euler method. And now we're going to say y of I plus 1 equals f0. So this is our f0 function. Use it in the following way. So we set the variable that we're solving for. In this case, it's going to be capital Y, using this at command. So we say at parentheses capital Y, and I do a space, and then we plug in our function. So y of I plus dt times 4 times capital Y minus y. Could we have simplified that function a little bit? You bet. Is this still going to work? Absolutely. Now what we need to do is plug in a guess for each step, and we just use y of I for this. So we're saying, okay, solve for the next time step and start from the previous time step. Usually works pretty well. And then we can specify some options for our solver here. And then we're going to end this. Okay, now what kind of options can we specify? Well, one you can specify is your solution tolerance. We're going to do this the following way. We're going to say options equals optimset tol of x, comma 1 e to the negative 06. Now you could change this value. This is basically a criteria on how close we have to get to the actual solution here before the solver stops. And this just is something we can use if we want to speed up or slow down our solver time. Okay, so there's our backward Euler method. Now we're also going to do the exact solution. We'll do that the following way, just like we did for the forward Euler. So y exact equals I plus 1 equals the xp to the 4 times t I plus 1. Okay, now we're going to run this. Let's press this. Okay, great. Everything's working, and now we're going to plot this. So we'll do figure 1, we'll do hold on, and then we'll do plot of y, t comma y, and we'll make these about blue circles. And then we're going to plot t of y exact, and we're going to make this, how about a red line? And we won't mess with the line width. That should be fine. Okay. Draw on our next label. Y label. YT. Title. Backward Euler method versus exact solution. And we'll throw on a legend here. Spell it correctly. So we have the backward Euler. And we have the exact. Okay. Unless I made any typos, this should work. Look at that, no typos. Okay, so here we have the blue circles, our backward Euler method, and the red line is our exact solution. So you can see the two agree pretty well. Now let's change our time step and see what happens. So we go to a smaller time step, as we would expect. Takes a little longer, but our solution is more exact. The blue circles pretty much line up exactly with the exact solution. And if we were to go in the other direction, say do a dt of 0.1, we're going to have more variation. So again, just like with the forward Euler method, it's important how we select our time step when we're approximating solutions to these ODEs.